Hi, I'm Raymond Lin, and this is Strategic Math. In our fifth lecture, we're going to talk about Gauss mark. We're going to talk about how to use some simple properties and solve 5 different questions. So this lecture will be much more simpler than the ones before and the ones that we'll present after. So let's just take a quick look at it and see it as a break. Let's first talk about how we define Gauss marks. We'll represent Gauss marks by putting square brackets around x. And for the simplicity of this video, we'll just call this as the function of x. So the answer for the function of x will be the greatest integer less than or equal to x. To understand how this works, let's look at some examples. The function of 7.2 will be equal to 7. But the function of negative 7.2 will be equal to negative 8. We can also put irrational numbers as x, such as pi. The function of pi will be equal to 3. But in our today's video, we'll mainly focus on x that are rational. Let's now take a look at some simple properties of Gauss marks. So if you go to Wikipedia, you can see many other properties, but today we'll just only talk about 2 simple ones that we can use to solve our questions. First is that we can represent x as n plus alpha, where n is an integer and alpha is a number between 0 and 1. This property might seem to be very easy, but it is actually very critical in the questions in the following. Our second property is that the function of x will be between x minus 1 and x. This actually seems quite intuitive, but again, it will play an important role in our third question. So let's now look at our question 1. It asks to prove that the function of x plus the function of x plus 1/2 will be equal to the function of 2x. Well, to prove our question well, we'll need to use our first property. And then the only thing we can do is that we'll put the question into different sections and solve for it. The first section is that if alpha is between 0 and 1/2, then the thing that we're going to prove will be right. If we then look at if alpha is between 1/2 and 1, we'll also see that this will be right. And this is how we prove our first question. Question 2. It asks to solve for x in the equation 2x plus the function of x equals to 3/6. Again, we'll use our first property to solve this question. By our first property, we can get that 2n plus 2 alpha plus n equals to 3.6. Notice that when we define x equals to n plus alpha, alpha is between 0 and 1. This means that in the equation, 2 alpha will be between 2 and 0. We can rewrite the equation to 3n equals to 3.6 minus 2 alpha. Because of this definition, we can get that this is between 1.6 and 3.6. That means 3n is between 1.2 and 0.53. This means that n equals to 1, alpha equals to 0.3, and x equals to 1.3. And this is how we solve our second question. Let's now take a look at our third question. It asks to solve for x in the equation x squared minus 8 times the function of x plus 7 equal to 0. So if we use our first property like above, we certainly won't get an answer because we'll get n squared and alpha squared, which is difficult to calculate. Instead, we'll use our second property. First, we'll rewrite the equation like this. X squared plus 7 equals to 8 times the function of x. This means that the function of x will be equal to x squared plus 7 all over 8. We can then put this into the equation. We'll then split this equation into two parts. What we'll get is that the function of x will be between 1 and 7. The other one we can get is that the function of x will be less than 3 and greater than 5. We can combine these two and get that the range for x is that it will be between 1 and 3 and 5 and 7. We'll then list out all the possibilities for the function of x, which is 1, 2, 5, 6, and then 7. We'll then use this to solve for every kind of x. Remember that x minus 1 will be less than the function of x less than or equal to x. This means that the only correct solutions for x will be 1, the square root of 33, the square root of 41, and 7. And this is how we solve our third question. Let's now look at our question 4. It says that k equals to the function of 106 over n. It asks to solve for the smallest positive integer k when n does not have a solution. N is a positive integer. So it seems that we can't use any property that we have talked about to solve this question. So let's do some observations. We'll draw a number line of k and write down the representing n's. So let's now look at n equals to 2. When n equals to 2, k will be equal to 53. Notice that n are consecutive. So this means that between 53 and 106, there will be no solution for n. We'll then look at another one, n equals to 3. It seems like when n equals to 3, this region also doesn't have any solution. And if we go on and on, we can see that this region will get smaller and smaller. So why not we go backwards? Let's look at what will happen if k equals to 2 and k equals to 3. It seems like that there will be a number of k's from 1 to something that will be consecutive. So if the problem asks for the smallest positive integer of k, this means that we have to find the first gap between the consecutive k's, which means that we have to find how many consecutive k's are there. Well, to answer this question, let's look at this one. If there are consecutive k's, it means that the difference between these two will be equal to 1. This means that when they subtract each other, it will be lesser or equal to 1. Let's simplify it, and we'll get that n will be greater or equal to 10. This means that there will be 10 consecutive n's. 10 consecutive k's. So if we want to find the smallest positive integer of k, we'll have to go further from n equals to 9, n equals to 8, and so on. So let's look at what happens if n equals to 9. We'll get that k equals to 11. When n equals to 8, k equals to 13. This means that the smallest k will be 12, and this is our answer. So let's now look at our practice problem. This is actually the same problem that we've talked about, but this time the number is 2021. So we've already know the reason behind how we can calculate the consecutive case and get our answer. So to solve this problem fast, we can see that we'll just put 2021 into this formula. What we can get is that n will be greater or equal to 44. So we'll then try what will happen if n equals to 44, 43, and 42. What we'll get is that the first unconsecutive case that occurs is between 45 and 47. This means that the answer for this question is 46. So let's now look at question 5. It asks for how many different numbers are there in the following. So it seems like that this is a totally different question that we haven't talked about. But we'll gain one intuition. We've already talked about consecutive case. So we'll know that in the consecutive case part, there will be a number of case, a number of different numbers that will occur. And in the parts where the consecutive case doesn't occur, we also know that we can subtract the ends to get how many different numbers are there. So we can easily see that the consecutive case will occur between 45 and 2021. We can also know that from 1 to 44, every n will gain a different k. This means that the number of k will also be 44. And this is how we get our answer. There are 88 different numbers. So let's do a quick review. From question 1 and question 2, we learned how to use this property to solve simple equations. In question 3, we've learned how to use this property to solve equations involving squares and roots. In our last problem, we've known that how to solve problems by counting consecutive case. And that's it for today. This is a simple lecture, and in our next lecture, we're going to talk about polynomials. See you then.